Hello class, my name is Tom Austin. This is my presentation on the research paper. And the research paper was on analyzing consumer product graphs. We will cover the basics of what the research paper was about, some background on graph theory, the analysis that was done, the new algorithm they came up with, and we'll get moving because we don't have a lot of time here. Title: Analyzing Consumer Product Graphs, Empirical Findings and Applications in Recommender Systems. The researchers were Zhang Hang, Pennsylvania State, Daniel Zhang, University of Arizona, Xinchen Chen, University of Arizona. Their goals were to use random graph theory to analyze bipartite or affiliation graphs, to study the way consumer purchasing evolves over time, to measure that compared to a randomly generated graph, and to create a new recommender algorithm to generate a graph in situations where clustering coefficients, and this is what they did, but it could be something other than a clustering coefficients, or other measures are sufficiently different than predicted by typical recommender algorithms. So a little background, we use graphs all over the place. Random graph modeling is used to capture mechanisms that determine the network topology, the way a network grows and its structure over time. And simple graph generation system can help us understand the way real systems work. Real networks, they generate consistent topologies. Some of the examples of measures we've got a short path between nodes, power law degree distribution, and a higher than normal clustering. We take a look at the bipartite graph, which is what they're going to be using. It has two parts. The consumers are the blue nodes, the products are the red nodes here, and the lines that go between the blue and the red nodes are the products they've purchased. And those are pretty much the properties of a bipartite consumer product graph. The bipartite consumer product graph in the previous slide, it exhibits a power law degree distribution, it has a high clustering coefficient, and it exhibits small world phenomenon. The classic random graph generation model, which is going to be used here, was developed by Paul Erdos and Alfred Renier, and it has been the foundation for analyzing statistical graphs. There are a lot of models that were derived from it. The particular model that's going to be used here is a model that will generate graphs and allow us to specify the degree distribution and the degree sequence to generate the graph. So we can, control some of the properties. Okay, we also are going to use recommender systems. Again, Amazon, half, Netflix, Yahoo uses them to get more customers, make the customers more happy. Anything to help. There's a lot of academic interest. Common approaches to the recommender systems include collaborative filtering. And one of the features of this is that it only uses the consumer product interactions. It ignores consumer and product attributes, or at least a lot of them. So we don't have all those other features. So that's the kind of data they'll be analyzing, which kind of makes sense. The particular algorithms that are going to be tried here in this research paper that, we'll talk about, they tried these. User-based, we identify similar consumers, we group them based on their past transactions and the product feedback. And a generative model-based, which we use variables to explain the interactions between the consumers and products. How are we going to model this? Well, we create a consumer product bipartite graph, as I had shown in the previous slide. In order to analyze it, we need to project it onto two separate unipartite graphs, one for consumers, the other one for products. An edge between consumers indicates that they've purchased at least one of the same product. An edge between products indicates those have been purchased by at least one common consumer. So we do lose information, but this is the This was at least the way they knew how to analyze them at the time. So here we see on the left-hand side a bipartite graph of consumers. You see the consumers there, and then different products they have bought. And then over on the right-hand side, you can see the projected graphs. There's only a few consumers, so we don't see a lot of edges there, but definitely we have edges all over between the products. But this is the way we know how to analyze it, so this is what will be used. Okay, there were two data sets used. One was a book data set by Taiwan's largest online bookseller. Another one was an online apparel data set by a US-based company. Again, the data was divided into test and training sets as we had done earlier in class. For the first test, they used a random graph model generator, the one that we talked about, that you can specify degree distribution and degree sequence. They measured the average degree, the path length, and clustering coefficient. In this case, the average degree was close. That's how you can specify. You think it'd be close. The average path length was significantly less, and the clustering coefficient was significantly less. You can see this in the graphs. The random is the pink, the real data is the blue, and you can see they're fairly close on the degree, but when we get to the average path lengths and the clustering coefficient, the randomly generated graph in the pink here falls short. That was the bookseller data set. If we look here at the retail data set, you see a little difference here. The degree wasn't quite on, but we also see these fall short for average path length and clustering coefficient. So maybe we can try something different. The random model versus the overall results. The real data had larger path lengths. The real data has stronger clustering tendency, as we saw in the previous slide. This confirms a recommender systems rule, which basically says consumer choices are not random. They can't be explained by a randomly generated graph. And we can see it didn't explain everything. We've got differences here still to cover. So the next thing they were going to do is test a real data set against the recommender systems. So they're going to evaluate the user-based algorithm we mentioned and the generated model algorithm we mentioned. And as we look here in this chart where they evaluated them, the user-based algorithm is in green. The generative model is in the orange. And as you can see, they come pretty close for the book data set. It looks like maybe the orange one, which is the generative model, is a little bit closer in terms of matching the real data. If we go to the retail data set, the degrees are pretty close. It looks like the user-based model is a little closer on the average path length than on the degree, and maybe even on the clustering coefficient. Falls a little bit more short on the clustering coefficient, which is what they focus on. What does that mean? Consumers and products tend to form cliques or groups in projected graphs. Previous research has shown short path lengths, large clustering coefficients are consistent with the hybrid random graph model. They tried a random graph model where you could specify degree and sequence. It still had significant deviation from the data, especially the clustering coefficient, which is what we're focusing on here. The recommender algorithms didn't solve the clustering coefficient deviations for the retail data set. It did for the bookseller data set. At least it looked pretty close. The current recommender algorithms, they notice, don't go beyond their immediate neighbor for generating the algorithms that predict, the graphs. So they wanted to do something about that, and they decided to use a partitioning-based recommender algorithm. They were going to partition the data into clusters by taking some edges out, cut the minimum number of edges, and also maintain similar number of nodes for each partition. And then after that's been done, then they're going to generate edges within strongly connected graph partitions, and they believe that will help get a larger clustering coefficient. So there's an example here of how they did that. You've got different groups or clusters. You got G1, G2, and G3 here, and the initial connections are in part B. Then you see they make a connection to C, which happens to be close to, G2 is close to G1 and C is the next closest node. Alright, and then as they move down through G2, you'll see they make connections to D and E. This continues, and that's how they add their edges, or at least a basic idea of how they're going to add their edges. So how did this work out? It provided a better recommendation on the retail apparel data set, worse recommendation on the bookseller data set. If we take a look at it here, they put it in a table, and the bolded numbers are the ones that are the most correct. If you look at the retail data set, you'll see that every set of bolded answers is under the partition-based algorithm. But also, if you look at the bookseller data set, you'll see that every bolded one, which is the most accurate one, is the generative model. So in one case, the new partition-based algorithm made better predictions, and that was where we saw the differences in the clustering algorithm versus the recommender algorithm. So it did do some good in that case. Their conclusion, okay, the new algorithm illustrates a process for evaluating and creating new algorithms. It wasn't just the fact that they had created one that could work better in that particular data set, it was how they did it. They used this random graph modeling based framework to look at deviations, and then they attempted to find better algorithms. They tried the recommender algorithms, and then they decided they were going to try and find something that would solve the problem with that clustering coefficient, and they did in that particular data set. So it's a good model to be used to analyze the data sets and to generate new ones possibly. The performance might be tied to the data set that's used. In other words, if you try it with another data set, it may not work. Anyway, that's the presentation. I'm happy to take any questions that you have. Thank you.